the recording again. Ah, the recording started this time. Okay, so we came in a little bit late, but just talked about the first exam. Okay, so if there's no questions, what I'm going to do today is I'm going to take some of the problems from the exam review problems that are posted on Blackboard and run through them. And specifically, I want to go through numbers 3 and 4. And the reason why I chose those is because they're kind of harder and encompass pretty much everything that we've done so far up to this point. Okay, so Ryan asked the question, will there be any questions like the last one on homework 2, or is that one too difficult? My philosophy is that I try to make the homework and the practice problems more difficult than the exam problems will be. So problem number 3 on the most recent homework, which is homework number 2, was particularly long. I would not expect, if I were you, a problem that were that long on the test. Okay? Is that a sufficient answer, Mr. Gallagher? Yep. Okay, good. All right, so I'm going to pull up the 2 practice problems I want to go over today, and I'll just remind you that both the solution and these practice problems are posted on Blackboard. So there's 5 practice problems here. It's basically, think of it like one additional homework, quote unquote, full of problems. So you should sort of see them on my screen here. A couple practice problems from lecture 1 and a couple practice problems from lecture 2. So I'm going to start with number 3 here. It's this disk spinning. And I like this problem because it involves both time-dependent kinematics as well as our relative acceleration and velocity equations. So this problem basically has like the whole kitchen sink to it. All right. And so that's part of the reason why I want to go through it, because it sort of like encompasses everything. So I'll kind of pause here maybe for a minute for people that haven't seen this or haven't given this a try to sort of copy down this particular problem. And I'll also copy the information over to my screen over here, and then we'll get going on this particular problem. Right now, the person who lives above me in this apartment complex is going through some exercise routine and is like pounding on the ceiling above me. So hopefully that's not coming through on the recording. Sounds like they're doing jazzercise up there. It's the most social interaction I've had. Okay, so we'll flip you guys over to the writing pad. We'll pivot. Where's my teams? Here we are. So let's move you guys over there. Okay, so we all should sort of be able to see the writing pad at this point. So I've copied some of the information down here from this particular problem. This picture here, which I'm going to draw some stuff on in just a second. And then also some initial information that we have. So initially, we're told that the angle here, theta, for this particular guy is at a value of 0 degrees. So we're sort of interested in what's going on with this particular point here, this point A. And initially, theta is 0, and we have some angular velocity of 0.1 radians per second counterclockwise. And we're told at time 0, so at t equals 0, we experience a constant angular acceleration, which here is in vector form. Alpha is 2 k hat radians per second squared. Okay, we want to determine the velocity and acceleration of point A at t equals 1 second. We're going to find the velocity at A and the acceleration at A at t equals 1 second. Second. All right, so there's a lot going on here. Let's kind of talk about the strategy that we're going to have to employ in this particular problem. So we're told that initially, which initially means t equals 0. It's kind of what initially means. Initially, we have some position of theta which is at 0 degrees. Okay, so with this picture, theta equals 0, point A is at this location. All right, that's pretty sort of easy to understand. And we have some angular velocity for the system that is 0.1 radians per second counterclockwise. Okay, so counterclockwise is this direction. So here we have, sorry, that's clockwise. Counterclockwise, so here we have 0.1 radians per second. All right. We're also told that this thing will begin accelerating at t equals 0 at 2k hat radians per second. All right, so this thing is also going to have some angular acceleration to it, which is 2 radians per second squared, also in sort of this positive k hat. Okay, so I'm curling my hand in the positive direction. My thumb is pointing out of the page back towards me. All right, it's positive value. So what this means is if we're interested in what the velocity of point A is after 1 second, we can think about the motion of point A because this thing is sort of rotating in this counterclockwise fashion, and we're also accelerating that rotation at a certain rate, that A is going to start over here at t equals 0 times 0, and it's going to move itself along the boundary over time to some other location which we don't necessarily know. Okay, so it is up to us then after 1 second to determine where has that point moved on this disk, and then what is the velocity and acceleration at that particular instant. So what we need to do is we need to figure out first where that point is after 1 second, and then we'll use our relative acceleration and velocity equations to determine what the actual acceleration and velocity is. All right, so that's kind of the strategy for this particular problem. All right, so let's go through that. Here we're given some initial conditions at time is 0, and we're looking for what's going on some later time, which is t equals 1 second. So when we're bringing time into these problems, you want to probably think about using that kinematic relationship that we have that exists between like angular acceleration, angular velocity, angular position, and time. And so those relationships that we have will utilize sort of these time derivatives that relate the pieces together. Okay, so here we go with our solution. So at t equals 0 seconds, we know that alpha, the magnitude of the angular acceleration, is 2 radians per second squared, right? So we can use this, and we're also told that it's constant through the problem, which is important. It's not a function of time. It's not changing over time. So this is generally our time-dependent relationship of alpha. It's just some constant value, okay? We also then can use the kinematic relationship that alpha is equal to the derivative of the angular velocity with respect to time, okay? And we can rearrange so that we have sort of our variables of interest on either side. So we can arrange this into alpha dt is equal to d omega. And now we can integrate this guy. So let's integrate. And so to integrate here, we'll set ourselves up an integral of alpha dt is equal to the integral of d omega. So alpha is constant through this problem, okay? And we're interested at what happens at time 0. And we generally would like to have some relationship of this angular velocity as a function of time. So I'm going to keep this general and say that our lower bound for this integral is whatever's happening at time equals 0. And our upper bound is going to be a general time t, right? Then the right-hand side here, we have the derivative dw, d omega. And at time 0, we're told that this guy has an angular velocity of 0.1 radians per second. So here the lower bound on this integral, matching the time, is going to be 0.1 radians per second. And then the upper bound on my integral is also going to be general, because I generally want an equation that relates the angular velocity omega to time, right? So when we go through this, we're going to plug in our actual alpha value, which is 2 radians per second squared, and you're going to end up with 2t is equal to omega minus 0.1 radians per second. All right, so radians per second on the right-hand side, basically radians per second for this whole sort of equation. All right, so this is what happens after we integrate. And this leaves us with an expression for the angular velocity as a function of time, which here will be 2t plus 0.1 radians per second. All right, some of you may go through this integration a little bit faster on your paper, but you have to be careful here that if you're told that the angular acceleration is a constant value of 2, if you were to just say that, okay, well then my angular velocity is just 2t. Well, you're missing your initial condition on your angular velocity, which is this initially has some angular velocity of 0.1 radians per second, which is sort of given in this problem. So don't forget about some of those initial conditions if you're doing integration, right? So we can have a similar sort of relationship between angular velocity and position. So similar for position, and that we know that the angular velocity omega is d theta dt. So you can kind of go through the same steps here and understand that at time is 0, theta is 0, because initially this disk is at the position theta equals 0. So we can sort of just integrate directly here and come up with the position as a function of time for this particular point is going to be t squared plus 0.1 t, and this will be in radians for our units. All right. So here is an expression that tells us basically the angular position of point A on this disk as it's spinning around. Right? Capiche? Capiche. All right. So now we're ready to sort of tackle our specific time of interest, which is what's going on after 1 second. So let's look at t equals 1 second, which is really kind of our time of interest for this particular problem. So here, theta as a function of time, if we plug in t equals 1 second, we're going to get 1 squared plus 0.1 times 1, or we'll have that theta is 1.1 radians, which is approximately equal to 63 degrees. All right. So this is telling us where that location of A is on our wheel. Okay, so after 1 second, this guy has spun around from position theta equals 0, which is sort of this general position here, to the position where we're now at 63 degrees, which I don't know, maybe is right about here. Okay, so A over 1 second time interval has gone from its initial position here to its position here. So here is location A, right? That's at 1 second, right? So this is where we are after 1 second has elapsed. And we've determined that angular position through these kinematic relationships relating acceleration and velocity. Okay, so we can also determine the angular velocity at this particular point. We have our expression for omega t, which for us, remember, is 2t plus 0.1. So here, omega at t equals 1 second is just going to be 2.1 radians per second. All right, so this is going to be a useful number for us when we go to our velocity calculations. All right, so here's my value of theta, and here's my value of omega. So this is kind of like reiterating the fact why I like this problem so much, because we have discussions of the kinematics before we even, the time, position, acceleration, velocity relations before we even get into like the relative velocity analysis. Okay, so now we're ready for our velocity analysis. All right, this is actually going to be kind of the easier part of this problem, and that is because we're relating the velocity of point A, which is what we're interested in, to another velocity on this body. And since this wheel is stationary at the center, right, this point O in the middle of the wheel is fixed, we can just write that the velocity of A is the velocity of O plus the angular velocity of this object crossed with the position vector locating A from O, right? Well, let's define some of these things. All right, the velocity at O we know is 0. The angular velocity vector, we kind of figured out its magnitude previously, but now let's actually go ahead and define it properly as a vector. So here, this is 2.1 k hat radians per second. And remember, this is specifically at t equals 1 second. So remember, this is specific to the time when t equals 1. At some later time, it's going to be larger because we're accelerating, right? So we have to be kind of specific here. The last thing we're going to have to do is we're going to have to define the position vector that locates A from O. And again, this is specifically at this time where t equals 1. And remember that our value of theta was 63 degrees. So we more or less, if we go back up to our picture here, we can kind of clear out some of the junk here. Remember that point A is about here at an angle of 63 degrees. So we can use the radius of this wheel, which is 200 millimeters, in that angle of theta to properly define our position. So here we have 200 millimeters multiplied by the unit vector that defines its location, which is going to be cosine 63 I hat plus sine 63 j hat, right? So if we actually work this guy out and put some numbers to this, we'll get that the position vector locating A from O here is going to be 91 I hat plus 200 sine 63, 178 j hat millimeters. All right. Some of you like to convert to meters. That's fine. I'm going to have to do that eventually because my velocity is reported in meters per second. All right. So we've defined everything now. Let's go ahead with our calculation. Our velocity then of A here is the angular velocity that we know here is 2.1 k hat radians per second crossed with my position vector locating A from O. I'll convert to meters here on the fly. So this is 0.091 I hat plus 0.178 j hat meters, or ultimately after executing my cross product. And a lot of people had cross product questions in my office hours, so please make sure that you practice cross products. We're going to be doing a lot of them, not just on this exam, but in exams to come. So a lot of cross products in this class. Please make sure that you have a solid method for doing it, okay? So after executing here, you should end up with negative 0.374 I hat plus 0.191 j hat, and this is meters per second. All right. So this is the velocity for this particular guy. All right. Looks like someone popped a question in. Check the chat here. Oh, nope, that's just Ryan saying yep. All right, sweet. All right, let's continue then. That's the velocity analysis. I usually advocate for velocity analysis first of the structure, and then we'll move to the acceleration analysis. All right, acceleration analysis, you're going to use your other favorite equation in your favorite class, right? Right. God, it's fun talking to myself. Okay, acceleration of O plus the angular acceleration of this object crossed with the position vector that locates A from O plus omega A O crossed with omega A O crossed with the position vector that locates A from O. All right. So here we are. We know that the acceleration of point O is 0 because this guy's fixed. So that's helpful. The angular acceleration, we're told in this problem, is constant for all time. So we can define our angular acceleration of this guy pretty simply as 2 k hat radians per second squared. All right. Our position vector locating A from O, that's the same as before. And again, this is specific for the time at 1 second. So here for us, if we just kind of bring this back up, it's 0.091i plus, I think it was 0.172, 0.178 j hat meters. And we also know that our angular velocity at this particular point is going to be 2.1 k hat radians per second. All right, so everything here is defined. We just kind of have to execute. Right? So the acceleration of A here is going to be 0 plus sort of the first component here is 2 k hat radians per second squared crossed with my position vector locating A from O, 0.091 I hat plus 0.178 j hat meters. This is my tangential acceleration term. And then I'm going to add to that my centripetal acceleration term, which is 2.1 k hat radians per second crossed with 2.1 k hat radians per second crossed with my position vector 0.091 I hat plus 0.178 j hat meters. Okay. One thing that you could notice if you want to sort of like take a little shortcut is you could notice that this cross product right here is the velocity of A. All right. So 2.1 k hat cross 0.091 I hat plus 0.178 j hat. That is exactly what we did up here. All right. So you could plug this velocity of A directly into that equation for this particular portion and go from there. That's perfectly fine. Either way, the way it's going to shake out is that your acceleration of A is going to be negative 0.756 I hat minus 0.603 j hat, and this is meters per second squared. All right, so there's your acceleration vector. We have any questions on this problem? Like I said, I really do like this problem because it's got the whole kitchen sink. We have time-dependent relationships where we're forced to use these kinematic relationships, and we're using both our velocity and acceleration relative equations. So I like this problem quite a bit. Questions? Questions? Okay. I'm also going to run through number 4. The reason, should we write units at every point? The more you include units, the less likely you are to make a unit mistake. All right. So I always encourage writing units when you're going through the problem. Keep the variables as long as you can keep the variables, and then when you're ready to plug numbers in, plug numbers in. So the strategy that I use on the writing pad is strategies that I would typically use if I were a student. So this is kind of like how I did all my exams, and I did well enough to get a PhD. So there you go. Okay. So let's continue now, and we'll work problem 4 from the exam review. And I'll pull that up. So here we've got a series of links, and we're told something about link OA rotates with a constant clockwise angular velocity of omega is negative 7 k hat radians per second. Determine the velocity and acceleration of the collar at B, which is attached to a horizontal frictionless rod. Okay, I like this problem because there are 2 links, and so you have to understand how to propagate velocities and accelerations between the links. And you also have restrictions on the motion of one of your particular points. So in this case, you have restriction on point B, as it's restricted to moving in only the horizontal direction. So these are things that you need to incorporate into the solution of your problem to have sort of a successful solution. All right. So give you guys a sec with this while I sort of copy it over. This problem also has a little bit of tricky geometry that you're going to have to work through, or I will work through for you here. Oh, sorry, I forgot to flip you over to the paper. My bad. My B. Nobody said anything. Can we see it? Okay, it's on Blackboard, so sorry about that. Okay, here's your problem. All right, so maybe another 15 seconds, and then we'll flip over and get to work. Okay. All right, so here we are. So this is problem number 4. Here we have this general setup, and we're given an angular velocity omega, -7 k hat radians per second, and this is specifically for a O, so I'll put that here. I have theta 30 degrees, and these geometric parameters h, b, and d are given. So we want to find the velocity b and the acceleration of b. All right, so away we go. And the general strategy here is we're going to sort of figure things out about link OA, and then propagate that information over to link AB by understanding that the velocity at point A on the two structures is the same. All right, so away we go. All right, here we go with our velocity analysis, and let's start at link OA. All right, so let's get right to it. The velocity at point A is the velocity at point O plus the angular velocity of AO crossed with the position vector locating A from O. All right, so we go up to our picture here. Point A, O is fixed, so obviously no velocity or acceleration at that point, so 0. Our angular velocity omega AO is given to us in the problem, -7 k hat radians per second. So it's kind of shown already in the negative direction, but there we are. It's moving with that general angular velocity. And then our position vector locating A from O is something we're going to have to define. So the position vector locating A from O. Here, the magnitude of the length of that link we're given in this problem as little b, which is 80 millimeters. Okay, so I'll convert to meters here, and we'll say this is 0.08 meters multiplied by the unit vector that defines that particular location, which will be cosine 30 I hat plus sine 30 j hat, or we'll get that the position vector of A from O here is 0.069 I hat plus 0.04 j hat meters. Okay, make sure you're okay with this position vector locating point A from O. I try to sort of enunciate that as much as I can, but make sure that you're starting at the right point and ending at the right point. Otherwise, you're going to have sign errors in your problem. All right. So we're ready to figure out our velocity of point A, which we're going to propagate then to the second link. So the velocity of A here will be negative 7 k hat radians per second, cross with my position vector that locates A from O, 0.069 I hat plus 0.04 j hat meters. And my velocity at A, after executing this guy, will give me 0.28 I hat minus 0.48 j hat. This will be meters per second. You can sort of like think about if this makes sense by going back up to your picture. We have some negative component in j hat, some positive component in I hat. So if we kind of like cruise back up here to our picture and think about what the motion of A about O actually is going to be, sort of this like fixed axis rotation, right? So it's kind of like moving along this circular pathway. And at this particular instant, it's kind of like moving in this direction. So some positive component in I hat and some strong negative component in j hat. So I think what we made there sort of kind of makes sense. So I like the solution that we have there. And it's always sort of good to double check. Again, if you're not quite sure about your cross product or worried about your signs, there you go. All right, so then we take this and propagate to the next link, which is length AB. And so let's look at link AB. And here now we're going to relate the velocity of B to the velocity of A. So we're ultimately looking for the velocity of B, which will be the velocity of A plus the angular velocity of link AB crossed with the position vector that locates B from A. We're always locating this guy from this guy, all right, B from A. All right, so we have a series of things here that we don't really quite know, all right? So a couple of things straight away is that VB restricted to I hat. So we'll say then that the velocity of B is whatever the magnitude of that velocity is. And this is going to be fully contained in I hat, right? We don't really know the angular velocity, so we're going to have to leave that as an unknown. For this particular link is whatever the magnitude is, but we know that it's restricted to k hat because we have planar motion. And the last thing that we have to define here is this position vector locating B from A. And this is kind of requires like an aside or a little bit of complication here. So the position vector locating B from A is going to maybe require a little bit of drawing here, right? So we go back up to this picture. Here's point A. We want the position vector that locates B from A. So we want this particular length. All right, we know the length of D is 100 millimeters. All right, so this is 100 millimeters here. But I don't really have the angle here between these guys. I don't have this angle. I'm going to have to do something else to sort of like figure my way through this problem. All right, fortunately, I do have this length H, and I do know this length B. So I can kind of create for myself a right triangle that helps me define some of these distances. Okay, so I'm specifically interested in like what would be this right triangle here to help me define the location of B relative to A. Okay, so this particular side here, I know is going to be a combination of H and also B multiplied by the sine of theta. Okay, so this side length here is going to be H, which we're given as 30 millimeters, plus B times the sine of 30 degrees, which we actually saw before. Here is B sine 30, which is 0.4 J, 0.04 meters, 40 millimeters. So this is 30 millimeters plus 40 millimeters on this side is 70 millimeters. So this is your distance that you have to go in J, so 70 millimeters down in J. And then this side length over here, we're going to leverage Pythagorean Theorem and say that this side length, if we're thinking about like a squared plus b squared equals c squared, this guy here is going to be the square root of the 100 millimeter side squared minus the 70 millimeter squared side length. Okay, or that this direction or this particular length in x, after you sort of like punch this into your calculator, is going to be 71 millimeters. All right. So there you go. This helps us to define both the y component and the x component of the position vector that locates B from A. And we have to be sure to say that it goes down in j hat and to the right in I hat. So this position vector that locates B from A, after kind of working through that triangle, is going to be 0.071 I hat, 71 millimeters. And we're going down in J, 0.070 J hat millimeters. Oh, sorry, meters. All right. So now we're ready to execute. And if we do this, we will have the magnitude of the velocity of B in I hat on the left-hand side is the velocity of A, which we saw for before, is 0.28 I hat minus 0.48 J hat. That's the velocity of A from previous analysis, plus omega AB K hat crossed with my position vector that locates B from A, 0.071 I hat minus 0.07 J hat meters. Right? So let's do our cross product. Okay. K cross J would give me a negative I, and we already have a negative, so I will end up with a positive value in I here of 0.07 omega AB I hat, and K cross I will give me a positive J, so I'll have an additional plus 0.071 omega AB J hat. I can separate this into I and J. Probably easier to start with J since there's no component of J on this left-hand side. We have 0 equal to negative 0.48 plus 0.071 omega AB. That's from here. And we can solve this guy to determine the angular velocity of link AB. Here is 6.76 radians per second, or in vector form. And this informs my other equation that we have here, and that is the I direction. And that is the magnitude of the velocity of B is equal to 0.28 I hat plus 0.07 multiplied by omega AB, which we now have, is 6.76 radians per second. You determine that the magnitude of the velocity of B is equal to 0.75 meters per second. And if you want to write this in vector form, we know it's contained to the x direction, 0.75 I hat meters per second. Okay, so there's your solution for the velocity. Unfortunately, we've run out of time for acceleration analysis, but I'll leave that to you. And the solution is posted if you want to kind of give it a crack, give it a go, and give it a try on your own. Okay, that's it for today. I'll stick around for questions if people have questions on exam. Make sure you review the exam instructions and you're ready to go at least a couple minutes before lecture tomorrow. Okay, thanks everybody for coming. I'll be responsive by email, and good luck with your studies.